Good afternoon. Thank you all for coming to my talk. My name is Yanzi. I'm a fifth-year PhD student from Kellogg School of Management. Today, I'll be talking to you about geographic resource pooling to balance waiting and traveling. This is a data-driven application to MRI hospitals in Ontario, Canada. This is a joint project with my supervisor, Professor Van Meegen, as well as Professor Hossein from University of Waterloo. So what is MRI? MRI, or known as magnetic resonance image, is one technology used by doctors to assist in medical procedures and research. It can detect various tumors within a human body and produce an imaging that's used by the doctors to diagnose as cancer. That is why our collaborating partner, Cancer Care Ontario, really cares about reducing the waiting time in MRI hospitals. So what is the history of medical imaging in Canada? As early as 2003, the Minister of Health already started to care about reducing waiting time in medical imaging sector of Ontario. However, 10 years later, we see from the review of the 10-year plan to strengthen healthcare, there is no significant improvement in wait time reduction. And it's of high importance that the province should take care to reduce their waiting time in the medical imaging sector. So in 2013, we came up with a handbook that regulates wait times in medical imaging sectors. In this handbook, we propose something called wait time target. And wait time target is an ideal time that the patient should be treated within. And the percentage of patients that's actually scanned within their wait time target is used as a performance measure to evaluate the performance of MRI hospitals. It is their goal to treat over 90% of their patients within their wait time target. However, by 2019, still less than 43% of the patients are treated within their wait time target, and the average wait time is over 58 days, which is much longer than the longest wait time target. So this is what motivated our research. How do we reduce the wait time? Well, the MRI hospitals in Ontario, now though connected under a local healthcare integrated network, are operating independently from each other. We want to find a way to improve the percentage of patients scanned within their wait time target using the data gathered from the 72 hospitals in Ontario. So naturally we thought, why can't we pool the resources together among the hospitals? But we know when we reduce the waiting times through resource pooling, we also increase traveling time. Especially for a province like Ontario, where the land is massive, the driving time between hospitals could be very large. So when we're faced with a trade-off, we want to answer two questions. How do we pool the hospitals together? And to what extent is pooling effective? With those questions in mind, we want to look at our objective function. This is our objective function. The first term over here is we look at the number of days patient J exceed his or her wait time target under a given partition. So of course, if we only want to minimize the first term, we would pool all the hospitals together, because with a larger resource pool, the wait time is reduced. And the second term we have over here is a driving time experience for patient J under partition P. Of course, given we don't have the home address of the patient, we use their current hospital as node 0. So any additional driving time incurred from the current hospital to the new hospital within the resource pool is an additional driving time. Of course, if we want to reduce that driving time, we don't want to pool any hospital together, because assigning a patient to their original hospital incur a driving cost of 0. But what we want to see in our research is a geographic pooling model, where we look at the trade-off between waiting and driving. What this means is we want to find a small partition of hospitals that we can pool together to reduce wait time, but at the same time, limiting the driving time within a reasonable range. How do we achieve this? Well, there's 3 things we need to do. First, we need to cluster hospitals together. Imagine we start off with 8 hospitals. The first thing we need to know is which hospitals should we group together. And in this case, this is a small animation, a small example of what we do in our actual paper. This hospital is clustered into 3 clusters. And what happens within each cluster? Well, we kind of pool their arrivals together. What happens over here is we take the 3 arrivals from the first hospital, 1 arrival from second, and 1 arrival from third. We group all those informations together and rank them according to a ranking mechanism proposed in our paper. Once all the arrivals are ranked accordingly, we need to route them back into each hospital. Given the rank of the patients, as well as availability in the 3 hospitals in the cluster, the patients are then assigned to the most suited hospital. This is an overview of what we do in our paper. I'm going to walk you through each steps of the scheduling, routing, and the clustering in our paper. First, I want to show you what is the data set we use. We use a data set from 14 regions, 72 hospitals within Ontario, starting on January 1st, 2013, ending on December 31st, 2016. This is over 30 million patient level record. What we have in this record is a hospital the patient goes to, the type of scan they need, the priority class of the patient, their wait time target, decision to treat, and actual service time. 2 things of notice is that decision to treat time is the time the patient arrives at the hospital and requests an MRI scan. The actual service time is the time him or her actually received the scan. So naturally, the difference between the 2 dates are the wait time. In an ideal world, we want the wait time to be shorter than the target time. Unfortunately, based on our data set, over 60% of the patients exceed their wait time target. So we have 4 priority classes, 1 to 4, 1 being the most urgent, 4 being the least urgent. And the type 1 patient have a wait time target of 24 hours, type of 2 have 48 hours, 10 days for type 3, and 28 days for type 4. We see that type 4 patient consist of most of the patient pool at 77%. Type 1 patient is only 2% of the overall patient. However, that class is of high importance because exceeding a wait time target for a priority 1 patient can have very dire effects. Now we know what the data looks like. The first thing we need to predict is arrival pattern. Because all the hospitals use advanced scheduling, we need to know what the arrival patterns looks like ahead of time so we can schedule the patients effectively. This is the arrival pattern of 2014. We see there are ups and downs. You might ask, is there any seasonality trend, weekly patterns, or monthly patterns we are observing our data? We check for all of those. The data does not exhibit any seasonality pattern, any of those patterns. You would see, can we use any standardized distribution to forecast arrival patterns? We check the Poisson process, normal standardized distribution, and a lot of standardized distributions. And none of them can predict arrival patterns with a high degree of accuracy. And most of all, they cannot capture the time series pattern and the dynamic pattern we see in the arrival. So we thought, can we use some machine learning technique to predict arrival patterns? Naturally, we would think recurrent neural network, so a machine learning method that forms direct graphs that exhibit dynamic behaviors of a time sequence will be a good way to capture the arrival pattern. We first looked at the traditional RNN model. However, it has a drawback. It cannot learn long-term dependency. What this means is that it's biased towards more recent information, and the prediction is highly influenced by the more recent data. However, our arrival pattern doesn't have such a problem because the more recent data should not have any bigger influence on the prediction than the previous data. So we thought, can we improve on the traditional RNN? Well, there's something called long short-term memory. This is a special kind of RNN that can capture long-term dependency. And long short-term memory can have up to 4 layers of data, and we can see it has a better prediction power. Well, we plotted the prediction in this graph. We see the dotted black line represent the actual data. The yellow line is the traditional RNN prediction result, and the green and the red line are 1-layer and 2-layer LSTM respectively. We actually ran the 3-layer and 4-layer LSTM, but it does not show any improvement in the results. We see that clearly the red line has the best prediction powers. However, one thing of great interest is that the yellow line actually have a very similar pattern to our actual data. However, the yellow lines just shifted to the right. That means the prediction power is delayed. This is due to the high bias towards more recent data, due to causing a lack in prediction ability. We used 4 different error checks to see which one had the best performance, and we see using any of those error checks, 2-layer LSTM outperforms all other ones. And we'll be using that to predict arrival patterns in our paper. We also run the same things on service durations. However, due to the time constraint, I'm not going to show you that here. Also, two-layer LSTM does have the better prediction power in service durations also. Now we have understand what the arrival pattern looks like. We need to know how do we pull the arrivals together. Well, we store all the arrivals in a centralized location, kind of like a super hospital. Then using those centralized locations, we rank the patients accordingly and assign the patients to the respective hospitals. However, the ranking is of importance. How do we rank them together and how do we schedule them? In our paper, we use a modified ranking algorithm that look at the patient's priority classes as well as the number of days they have already waited. Balancing those two, we rank the patients accordingly. Due to the limit time of the talk, I'm not going to walk you through the ranking algorithm and the scheduling algorithm. The scheduling algorithm is just a standardized advanced scheduling with a modified priority ranking. So with that, we need to answer the key question of our paper. How do we determine which hospitals do we cluster together? We proposed the objective function at the beginning of our talk. But with that objective function and 72 hospitals in the data set, what method can we use to cluster them together? Well, the two standardized ones are set covering techniques and KNN. In a set covering problem, we exhaustively search through the 72 hospitals to find a partition that minimizes the objective function. The problem with that is the high computational complexity. And most importantly, the exhaustive search in set covering problem cannot handle 72 hospitals. KNN is another method that can use to cluster hospitals together. However, it's prone to converge to a local optimal, and it also have a very high dependency on the initial choice. In our paper, we use something called genetic algorithm. This is a machine learning technique that takes in advantage of set covering problem and KNN while have limited downsides. The advantage is it does not get trapped in a local optimal that often, and it can handle the 72 hospitals. So using genetic algorithm, we can find a good clustering technique. This is two graphs we get from applying our objective function to our data set with a different trade-off coefficient. The one on the left have a trade-off coefficient of 1/5, and the one on the right of 1/10. The blue line represents the driving time, the red line represents the exceeding time, and the green line will be the summation of those two lines with a different trade-off coefficient. And we see the minimum point on the green line will represent the optimal clustering. So we can see, using our objective function and a clustering technique, we can find the optimal cluster of different trade-off coefficients. Now we know how do we cluster them together. What does a cluster actually look like? This is a map of Ontario. The small pins on there represent each of the 72 hospitals. The pins of the same color represent they're in the same cluster, and the pins of different represent they're in the different cluster. We can see in the remote area on the top left-hand side, they are clustered together. However, there's an interesting insight. When we zoom into the map to the center of Ontario, which is Toronto, this is the busiest part of Ontario. We see the hospitals over there are actually not clustered together. This is due to the fact that these hospitals have similar arrival patterns, similar utilization, and they're all heavily utilized. So grouping them together does not take a full advantage of resource pooling. But when we're dividing them to nearby regions and combine them with less utilized hospitals in the remote areas, we can take a full benefit of resource sharing while still limiting the driving time within 2 hours. So now we know what our clustering look like, how much wait time reduction can we achieve. This is a table summarizing our results. The blue line is what happens in the empirical data. We see that 60% of the patient exceed their wait time target. The orange and the gray line are when we use the standardized queuing model of first come, first out and non-preemptive priority queues. The yellow line is when we use our proposed ranking algorithm and geographic pooling. We can see that under our model, we were able to reduce the percentage of patients exceeding their wait time target to 34% without any capacity expansion. But remember, at the beginning, we talked about it is a goal of the hospital to serve 90% of their patients within their wait time target. Well, we need some capacity expansion. If we don't use any resource sharing, we need at least 50 scanners to achieve an average service rate of 90% in the hospitals. And we need 72 new scanners to achieve a 90% service rate in each of the hospitals. But if we use our geographic pooling, we only need 8 more hospitals. This means with a smart scheduling and smart ranking, resource pooling can achieve a significant wait time reduction with a small cost in capacity expansion. So what are some insights and contributions of our paper? First of all, we provide an accurate prediction model that captures the arrival pattern as well as the service rate of a very robust and noisy data using recurrent neural networks. Second of all, we propose a geographic pooling method that can reduce the percentage of patients exceeding their wait time target by 30% using genetic algorithms. Lastly, we can propose a strategic capacity expansion recommendation to reach a 90% service rate with very small capacity expansions. We provide a feasible and easily implementable resource sharing model that hopefully will be used by the Ontario government to reduce their waiting time. With that, I conclude my talk. I thank you for your attention and open the floor for questions.